Hi guys, today we are going to train a diffuser model or a DDPM for unconditional image generation. I'm going to use Huggingface's official tutorial here as a reference. I will change it slightly to make it more user-friendly and explain the process. I will put a link for the official tutorial in the description. Through the process, we will use Huggingface's Diffusers and PyTorch. Paper that the model is introduced is Denoising Diffusion Probabilistic Models. I will put a link for that too. However, this is more of a practical video, so we won't get into the paper. I will put the GitHub link to this notebook below in the description. And as usual, if you like this video, subscribe to my channel, like this video, comment what you want to see next, and let's just dive into it. I am using Kaggle notebook because of its GPU support. However, you can use whatever you want. You can use your local computer, you can use Google Colab, I don't care. Let's get going. The first thing we are going to do is we are going to install diffusers. So we can do this by pip3 install diffusers and enter it. After diffusers have installed, we are going to import some libraries. We will start with Torch, and we will from Torch Vision import transforms for some data augmentation. From torch.utis.data, we will import data loader to load our data loader. From torch.nn.functional as f, because this is import, we will use this f to find our loss function. From torch.optim import ADAMV as our optimizer. Now we will start import from diffusers. We will from diffusers import unet to the model, which is the backbone of this algorithm, unet, and we will have DDPM scheduler. This is to add noise to our images, and DDPM pipeline. And we will use this to generate images in an easy way. After that, from diffusers.optimization, we will import get cosine schedule with warmup. This will be used to dynamically change the learning rate while the training is happening. After that, we will from dataset import load dataset, because we will use it to load the dataset. After that, we will import accelerate import accelerator. We will use accelerator for two things. First is gradient accumulation, and second one is mixed precision. We will use it to apply them to our training loop in an easy way. To load the images, we will import pill, we will import image. From tqdm, import tqdm for a pretty progress bar. We will need numpy as numpy, we will need random, and we will need time it. And let's run these. This is in a new line, of course, cannot import loader. This is just optimization from datasets. So we did our imports. Now it's time to define some hyperparameters. First of all, we will need random seed, which I will say 42. This will be used to make the code reproducible. We will need image size. We will resize our images. I will call it 128. And we will need batch size. This is dependent on your GPU. For this, I will say set it to 16. Learning rate is 1e-4. Number of epochs, I will set it to 50. It just generates good enough images. Number of generate images. What this is that we will create a function and we will say generate this number of images. So I want that function to generate 9 images per call. So it is that. And after that, number of time steps. This is to denoise the image. The higher is better in trade-off with latency, okay? But the default is 1000, and I think 1000 is just fine. We can keep it 1000. Mixed precision is FP16, okay? And gradient accumulation steps is 1. We will give those to accelerator. After that, let's set some random seeds. Random seed, okay, we will make it np numpy.random seed. After that, torch.manual seed random seed torch.qda.manual seed random seed torch.qda. Just copy this seed all random seed and torch.backend.qdanon.deterministic equals to true. Qdanon benchmark, we will say benchmark is false. After that, we need to know which device we are working on, if it is GPU or CPU. So for that, we will use device equals to qda if torch.qda.is is available, else CPU. So if we have a GPU, it will be qda. If we don't have, it will be CPU, and let's run the cell. Torch no attribute because there is k backends. Now we will load the dataset. For that, we will say dataset equals to load dataset. For that, we will use this dataset, this butterfly dataset, and we will say split equals to train and enter. Before we move on, one addition, we will add import matplotlib.pyplot as plt. And after that is done, let's visualize some images. Figure and axis equals to plt.subplots. We will use one row, 4 columns and 4 images, and we will say figure size equals to 16:4. For eye and image in enumerate dataset, we will use 4 images, so we say 4 and we take the images. We say axis eye and we will show the image. Again, axis eye and we will set axis off and we will show the figure. Run this. Axis is not defined because this is axis and figure show. Okay, as we can see, these are our sample images. Next step is we will apply some transformations to images for both data augmentation and to resize the images. For that, we will use Torch Vision's transforms. So we will say preprocess equals to transforms.compose. And we will just type in the operations, okay? Transforms.resize, we will start by resizing. We already defined our image sizes. We defined them as image size, not just say img size, okay? Image size and image size. Transforms.random horizontal flip. Guess what? This flips it horizontally randomly. After that, we will put it to tensor and we will normalize it with 0.5, and 0.5. Let's just run this. Now we want to apply transforms to our dataset. For that, we will create a function called transform and we will say examples as input. So we will create image list and we will apply preprocess function. We will convert the images to RGB format with 3 channels and we will apply it for every image in examples image. Okay, and we will just return it as a list. Images, image. Let's call it images. Okay. And we will actually apply that with dataset.set transform. This applies this transform.compose to all of the images in our dataset. Next step is we will create a data loader from PyTorch so that we can iterate through the dataset in the training loop. So we will say train data loader equals the data loader. We will say dataset and we will say batch size equals the batch size and we will say shuffle equals the false. What this does is this will be our data loader in PyTorch. Let's run this. Okay, so dataset is ready. One quick thing I want to add is that, for example, in this case, we have dataset, right? We just said load dataset and it just became ready to use to us. So what if we want to, apply the images from our local computer, or we have a file which contains images and we want to iterate through them and create a data loader with them, train the model with them. How we are going to do is, the easiest thing, I guess, is to create a PyTorch dataset and apply all these in the PyTorch dataset, which will be the same thing. If you are curious about this, I did the same thing in UNet implement from scratch video. We can check it out from somewhere around here. Okay, I will put the link in the description. If you want to train this with your local images, just copy the same procedure, dataset creation procedure from that video, and you are good to go. Now we will continue with the model definition. Model equals the, as we mentioned, the backbone of this is UNet. UNet TD 2D model. We create that and we will give some arguments. Okay, one of them is image size, which denoted as sample size, image size, input channels. Since this is an RGB image, we call it 3. Output channels, we want RGB image, so we call it 3 again. Layers per block, we will call this 2. And we have block out channels. We will use just the 128, 128, 256, 256, 512, and 512. By the way, I won't go into detail of these parameters of UNet or how UNet works. It is out of the scope of this video. In this video, we just train the diffusers. But if you're interested, and if you want to go deeper into that, which I recommend, you can check my video of implement UNet from scratch. I will put it around here and link in the description. So make sure you check that out, and I won't go into details of the UNet parameters. But if it is ready to use, you can just take this and use it, okay? So we have down convolution and up convolutions. So for down block types, what we are going to use is that down block 2D, okay? And we will use 4 of these. 1, 2, 3, 4. And after that, what we are going to do is attention down block 2D. One more down block 2D. And this is our down convolutions. Now it's time for up block types, which is similar. Instead of down, we use up block 2D, attention up block 2D, and 4 of up block 2Ds. Okay. And this defines our UNet model, and let's just initialize it. Model.toDevice and put it to device. Let's run this. It ran successfully. Now, after you create a model, whether you implement it yourself or use a function, it is always a good idea to check if it works or not. And that is exactly the thing they did in the official implementation, which I am taking the reference. So how we can do is, just like we did in the from scratch series, we create a sample image. Okay, we can just zero element of the data set and take the image. Okay, and we will unsqueeze it. What this unsqueeze does is that it adds a dummy batch size of 1, and we put it to device. So let's first print out the input shape. Okay, this is sample image dot shape. After that, we are going to print output shape, and we expect them both to be same. So it will be output of the model, which given sample image and time step equals to 0. Now we give time step equals to 0, but we will change that, of course. By the way, I changed this not image but images, and this is sample image. I removed the S. We want its shape, which we do it with sample.shape. By the way, this is images, and let's just call this sample image since it is just one, and run this. As you can see, we have the same shapes, so model looks fine for now. Now let's continue with actually defining the schedulers, noise schedulers. What it does is that it makes the image noisy, okay? It adds noise to the image. So for that, let's call this noise scheduler and take it from DDPM scheduler. And we have number of training time steps. We defined it as number of time steps, which we set 1000. Like I mentioned, if this is higher, your images will be in better quality, but it will take more time to generate. Let's create a noise torch that's random, and so this may look similar to what we did with DC GANs, because it is similar. And we put this to device. This is our noise tensor. And we will need time steps, and for now, since this is dummy, we will just say long tensor 50, and we will put it to device. Okay. After that, we will apply the noise to the image, which is noisy image equals the noise scheduler dot add noise sample image noise, and we will add time steps. Now let's visualize the noisy image. For this, what I will stick to the reference image that from array we will noisy image, we will permute it. So what it does is it changes the channels 2, 3 to 1. We will add 1.0 and we will put the space here. 227 plus .5, and we put it to CPU, and we take it to NumPy, and we take the 0th element, and I forgot that this you have to change its type to unsigned integer 8, and this is how a noisy image looks like. Okay, now let's define our loss function. So let's say our predicted noise, okay, we will say model noisy image, we will give this as input, and we will give this time steps, and we will take a sample of it, and the loss will be defined as f dot mean squared error loss, and we will give noise spread, which is the output of our model, and the noise itself, and this will give us the loss value. And actually, let's print the loss. We can see it just works fine. We are slowly moving to the actual training, but before that, let's see how we can show images. Okay, so we will create a function to show images. Let's call this sample image generation. Okay, we will take model as input, we will take noise scheduler, we will take number of generate images, how many images we want to generate, we will take random seed, and we will take number of time steps as input. So here we have to define the pipeline first, DDPM pipeline. So this is just makes it easier for us to generate images with this pipeline. And we unwrap the accelerator model, okay, when we give the scheduler equals the noise scheduler, and we will say images, which will be the generated images. To pipeline, we will give several arguments. First is batch size, which is the number of images you want to be generated. In this case, it is number of generate images, which we gave in the beginning as 9. Where is it? Here. Okay. After that, we will do a random seed torch.manual seed random seed, and we will do number of inference steps. We set it to 1000 again during the hyperparameter definition part, and I think 1000 is just enough, and we will take the images. Now this is images. Now we will just plot the images. Okay, for that we will create a figure, plot that figure. And for I in range 1, 2, number of generate images plus 1, because we started with 1, and if we have 9, we want to go until 10. And figure that at sub plot. So in this case, I want it to be 3 to 3 grids. Okay, so in total of 9. So I will say 3, 3, 3, 3, 3, 1, and I will say im show and images I minus 1, because we started with 1 instead of 0. And we will just say plot.show. So we are going to use this during the training because we want to see how image generation improves, and also we will use it in the inference part if we want to generate images on our own. If we have any errors in this part, like typo of stuff, it will come out in the training loop part. We will come back and correct it. Initial thing, I realized this is with small letters. Time steps. Now we will go with the actual training loop. Let's start by defining our optimizer. So we already defined ADMV. We say model.parameters, we give the model, and as learning rate, we have a learning rate we define in the hyperparameter definitions. We will need a learning rate scheduler. This is not a must, but it is good to have, okay? So it's just like during the training, it just adjusts the learning rate for you, okay? So we will use cosine schedule and with warm up, okay? For optimizer, we will say optimizer, we will say number of warm-up steps, we will give it 500, and number of training steps is just length of train data loader multiplied by number of epochs, which gives us the number of training steps. Now we define accelerator for gradient accumulation and mixed precision. So mixed precision equals to mixed precision we define in the hyperparameters. Gradient accumulation equals to gradient accumulation steps. This is also steps that we define in the hyperparameter section. Now we have to put the model, actually everything to accelerator. Okay, for that we say model, optimizer, train, data loader, and learning rate scheduler to accelerator that prepare. We say model, optimizer, train, data loader, the same order, learning rate scheduler, and that's it. Now I like to estimate how long did the training took. So what I will say is start equals to timeIt that default timer, okay, and start it. Now we are getting into the training loop. So for that we will iterate every epoch for epoch in TQDM range of number of epochs. We want the progress bar to stay instead of printing a new line. In notebooks, it may, instead of staying the same, it may print it as a new line. To change that, we will give two arguments, position equals to 0 and leave equals to true. This is purely cosmetical, okay. We will get the model to train mode, and we will say train running loss equals to 0. This is where we will keep the loss in. So we will start to iterate the data loader. For index and batch in enumerate, we use TQDM again, and we will iterate through train data loader, and again to prohibit it from printing new lines, we say position equals 0 and leave equals to true to TQDM, and we will start to get images. Clean images is inside batch. We will take images up images, and we will put it to device. This is a batch of images, okay? And what we're going to do is we say last batch size, we will have a parameter like this, and we will get length of the clean images. So what it returns is that the length, it returns the batch size, okay? For example, our batch size is 16. In all cases, it will return 16 to last batch size. But in the end, for example, we didn't have 16 images in the end, but instead we have 10 images. In that case, it will return 10 to this. So why it is important is that we will create other things, such as noise, according to this batch size. If we just use our hyperparameter batch size, in that case, it will be a dimension mismatch in between the tensors, and it will give us an error. So we have to get the batch sizes in every iteration for that, because mostly the last one is different. Now we will create our time steps. We do it by torch.random integer. We will do it with zeros. We will use noise scheduler .config that number of train time steps. Okay, and we use last batch size. Okay, and we will put it to device. And after that, we will create our noise images in this case, because they are batch of images. So we take noise scheduler that add noise just with it in the previous cells. Add noise. We will put clean images. We will put noise, but I forgot to define the noise. So let's come here and define the noise. Noise equals torch.random n clean images.shape device equals to, actually we don't need this. We just say that to device. Okay. We have the noise now, so we add the noise and we add time steps to the noise images. Okay. Now it's time to apply the learning. For that we will use accelerator. So with accelerator that accumulate, we give model as input, and the rest is we do everything the same. Okay. So our prediction will be noise pred. We will say model.noisy images time steps and return dictionary equals to false, because we don't want that. We just want the zeroed output. We say loss equals to f.mse loss. F that means squared error loss, and we say noise pred, which is the output, and our gold, which is the noise. And instead of loss.backward, we will do accelerator.backward, because we are using accelerator. So we put the noise, and we will do some gradient clipping. Accelerator.clip grad norm, and we will do model.parameters 1.0 and optimizer.step to be sure learning is happening, and we have to update learning rate scheduler.step, and at last we have optimizer.0 grad. So it's just like a regular PyTorch training loop with small modifications. So our train running loss is plus equals to loss.item, and our loss for whole epoch is train loss, and it is train running loss divided by index plus 1. Okay, so let's take the last learning rate. Train learning rate equals to lr scheduler that get last learning rate, and this actually returns a list of one value, so we get the zeroth of it, and we say we will print the values. Okay, we will print train loss for epoch, so this is for epoch plus 1, and train loss, I just want the 4 values of the float, so I say that for f, which is enough. And we will put learning rate, train learning rate. We want to keep an eye on the learning rate too. And we just say train learning rate. Okay. And in every 10 epochs, if epoch modulo 10 equals to 0, we want to show images. For that, we will use our sample image generation. We will give model, we will give noise scheduler, we will give number of generate images, we will give random seed, and we will give number of time steps. So what it's going to do is that in every 10 epoch, it will take our model, it will go to this function, it will take our model and create 9 sample images for us, so that we can see the progress of the model. So why in every 10 epochs? Because it is very expensive to generate images, and if you generate in, I don't know, in every epoch or every 2 epochs, the training becomes very long. So I found it is optimal to generate it in every 10 epochs. So let's stop the timer, time it.default timer, and let's print it. Training time, we will do stop minus start that to f seconds, and we will print it. And we will run this. So we have a typo. This is not accelerator, this is accelerator. Now the training is started, and let's meet here when training ends. So I did a typo in this sample image generation function. Instead of 1, it's supposed to be I. And let's run this. Oops. Let's run this, and let's run the training again. Now our training is complete. Now let's look at the results. So as you can see, the loss started at 0.08 and it is decreasing constantly. That is something we want. And as you can see, the other thing, our learning rate is constantly changing if we go to the end of the training. Now let's look at the interesting part, which are the images. At the 0th epoch, while the model is trained just for 1 epoch, these are the resulting images we have. And at the 10th epoch, we can see a butterfly, something like butterfly. At the 20th epoch, we can realize that it is actually butterfly. At 13th epoch, it becomes more realistic. At the 14th epoch, we have more variety and they are even more realistic. And now we will do the inference and check the latest results of the model. For that, we use the sample image function here to generate images. This one we will call this. So what we are going to do is sample image generation. We will give model, noise, scheduler, number of generate images. We want 9 of them. We gave random seed and number of time steps. And we will wait for that to generate our final images. And these are the inference images with the latest trained model. So if you want better images, probably training with more epochs will help. Also, I suggest playing with learning rates and number of time steps. As we discussed, if you want to train with your local images, you have to create a dataset. You can use the one I used in my UNet video and train with your own images. And this is how we train the diffusion models. Done.